Good morning, everybody. Welcome to Codeforce's round 656. It's a Div3 round. I wasn't able to compete in the round today because I had to give a lecture at the same time. So unfortunately, I won't be actually typing the solutions, but I thought it might be helpful for me to go over the solutions since I had a couple minutes where I wasn't really needed. So for problem A, you are given three integers, and then you're given these x, y, and z, and you want to find an a, b, and c, where the max of the first two is going to be x, the max of the first and third is y, and then the max of the second and third is z. So the condition that you need to satisfy in order for this to be true is that two of the numbers have to be the same of these two, because whatever your max is going to be that bigger number. And then in addition to two of your numbers being the same, you also need the condition that the third number is smaller than that. And then you can just casework which two are the same, and that's going to be one of the values. The other value will be the smaller value, and the third value will just be, I guess, the smallest one as well. So yeah, that's problem A. I don't really think I need to draw a picture for that. It should be pretty self-explanatory. For problem B is a pretty easy problem. So for problem B, you're given, like, you've got some permutations. Maybe it's like one, maybe your permutations are like 1, 2. Like one, maybe it's like 1, 2, 3. Maybe that's your permutation. So what this might be when you combine multiple copies of this, when you interlace them, rather, it might be like something like this. Like maybe this is 2 copies. So now the first thing to notice is, let's just look at the first version of each copy. We can do that, like the first one, the first 2, and the first 3. And this order actually uniquely defines what the permutation originally was. Since all of the permutations are the same order, we just need to find the first time that each number occurs. We can sort the numbers by that, and that's our original permutation. The proof for that is pretty, I guess, not too hard to do. But I think it's like easier to prove if you just do a couple examples by hand. You could also do the last instance of each number, and it's like a symmetric problem, so there's no reason one of those would work and the other wouldn't. All right, cool. So that's problem B. Let's look at problem C. Make it good. So you're given some array of n integers, and you want to find the length of the smallest prefix, so that if you remove that prefix, the array is good. So first of all, let's talk about what a good array is. So maybe the array, let's look at some example maybe. This is a good example. So the array like 1, 2, 5, 7, 4, 3 is good. And the reason is you can remove the first and the last element each turn and append this to the end of our answer. And we want our answer to be in sorted order. So what our answer would be is it'd be like 1, 2, 3, 4, 5, 7. Now, if we want to figure out how to actually do this, it's pretty easy. You just compare these two and remove the smaller of them. So now the natural question that follows is, what sort of arrays have this property? What sort of arrays are good? And if the smallest is always on one of the two ends, that means the values need to be increasing and then decreasing like this. So what we can do is, if we know this is what the array that we're looking for, if we have all of the elements in the array, we can look at them from the back, and then we want to see, all right, how long does it increase? And then once we get to the first decrease, we want to see how long does it decrease. And when it increases again, if it ever does, like let's say it increases between these two numbers for the second time, then this is the part of the array that we have to remove, because the array that's left needs to be an increase followed by a decrease. Okay, awesome. So that is, that's this problem. Fantastic. Let's look at the next problem then. Problem D. A good string. Yeah, okay. So if you have a good string, the string is good if it's like half A's and then the second half is a good string for B's. So I'm not really going to go through the logic of how you would arrive at this, because it seems, I don't know, to me it seems like just like one instinctual thing you want to try. But basically, what you can do is you can do a DP where your state is both where the beginning of this like string that we're interested in is, and then also the length that we're interested in. And from that length, we can figure out what letter it needs to be based on the final length. So we can do some DP, and the DP would be DP at some index, and then some like power of 2 length. Now, like if this is going to be 2 to the 5th, right? We can just store 5 here. And that would like be equivalently, like every time we want to use this, we would just use 1 left shift 5 instead. Fantastic. So that works pretty well. Now, how do we actually do the transition to this DP? So there are 2 things this can lead to. We can either like use the first half as all A's, or we can use the last half as all A's. So we just want to be able to quickly check, all right, is half of this all 1 character? And we can count how many A's there are in any substring of the array by, if we've got like some A's and maybe some B's, like it doesn't matter what these letters are, they're just something else that isn't an A. Maybe I'll just use dashes instead. That might be, oops. So maybe we just have like some things that aren't A's. So we'll do 26 different arrays, 1 for each letter. And we'll do like a cumulative sum of a 1 if it's an A, or a 0 if it's not. And now if we do some range sum here, that'll count how many A's are in this range. So we can basically count in this range how many A's are there, and we can see if this range is all A's or not. So you can do a cumulative sum for each letter, and then you can easily answer this DP. Now, since this DP is like very limited, I guess, in what it does, you can probably just not even do the DP. You can probably do just some recursive solution instead, and then you don't really even need to memoize. But I think the DP is like easy to think about, so if I were actually competing, I would probably just go write it immediately rather than maybe stopping to think of a more, like a cleaner solution. But it would require more thought, so it might take me longer to solve. All right, cool. So now problem E. Here's where things kind of start to get interesting. So you're given some graph with some directed edges and some undirected edges. And you have to find some way of either directing all of the edges so that the graph is acyclic, or determining that it's impossible. So let's imagine we just already have some directed acyclic graph. Maybe it looks like this. If we have this graph, if you can imagine that we have a top sort of it, maybe our top sort is like 1, 2, 3, 4, 5, 6, 7, 8. So a top sort is like some way of ordering the nodes where for any direction of the edge, it goes from smaller to bigger. So we can do a top sort pretty easily by storing some queue of nodes that have 0 in degree. And initially in that queue, we'll have just these 2 nodes. And as long as that queue isn't empty, what we'll do is we'll empty the queue. Or we'll like look at the first thing in the queue. We'll subtract 1 from this thing's in degree. And if it turns into 0, then we'll add it to the queue. Then we can remove this. Hardly. So sorry, I've got a Zoom call going on I have to kind of pay attention to. So then we do the same thing for this 2 node. And now this node we don't add to the queue because currently it still has some in degree. So we can continue doing that, and then we'll get like some top sort order like this. The order that we remove these nodes will be the correct order for some top sort. If the graph has a cycle like this, then there is no top sort, because we'll have these 3 nodes that never get removed, So we won't be able to find some way of ordering them that's legitimate. So it should be pretty clear that if the graph already has a cycle, then there's no way to direct the rest of the edges in order to remove that cycle. The cycle is always going to exist. But if the cycle doesn't exist, then what we can do is, that means there's some top sort of the nodes. So if we can make that top sort, then what that lets us do is any future edge that we don't know, we can just direct it in the correct direction that matches the top sort. So that's like one solution, pretty constructive, and shouldn't be too difficult to implement. Like as soon as you have the top sort, you just compare the two endpoints of each edge. All right, awesome. So there are two more problems. Problem F, I'm not totally confident in my solution of. My main idea is the following. So if we have some tree, I think a greedy approach might work here if you do the greedy approach correctly. And what I think we would do is on each turn, we're gonna initially look at all things that are like almost leaves. So we have a bunch of leaves. Here are all of the leaves. We're also going to consider the almost leaves. So the almost leaves are things that have exactly one edge that isn't a leaf. And that's these two things. So what we can do is we can sort these almost leaves by their degree. So like it makes sense that we want to remove the smallest almost leaf first, or we want that to become a leaf as soon as possible, because then we have more freedom as soon as possible in the next turns that are possible. This one, it might take us more turns. Since it's got more leaves, it might take us more turns in order to access this extra leaf. So we might not be able to activate it as early as we would like. So I think what you can do is I think you can sort these by, you can have them in a priority queue by their degree, and then you can repeatedly remove from the smallest almost leaf if you can. If for whatever reason you can't remove from some almost leaf, then you would have to remove these leaves here. And then that would create new leaves for you as well. And this would also create new almost leaves. So yeah, I don't have a proof for why that would be right. And it's possible that's just not right. It's possible that's just a wrong answer. And I guess I would figure out more about it if I were actually competing in contest. So maybe that's a good thing to read the editorial for or look through the comments. All right, awesome. And then the last problem is this column swaps problem. So this is a very interesting problem, I think. I also don't think it's quite as bad as the scoreboard would make it look. But the samples, I think, are pretty good. So let's look at this sample here. So it's 5, 3, 5, 1, 4 on the top. And then on the bottom, it's 1, 2, 3, 2, 4. The problem is, on some turn, what you can do is you can take you take one column and you can swap the two elements in it. And it says you can swap each column at most once, but there's no reason to choose a column twice because that's just undoing the same move that you did originally. So if you can choose each column once, like, you would only want to choose each column at most once anyway, so that constraint doesn't actually matter. Now, for these other constraints, or for like the other constraint is, after you do all of your swaps, you want each of these to be a permutation. So you want each of them to contain the numbers 1 through n. So, okay, so how do we actually do this problem? The first observation is it's going to be impossible only if you don't have like the right number of numbers. So you need 2 of each number between 1 to n. So you can do a counting sort initially, and if that's not the case, like if that doesn't work, then it's going to be impossible. Because you need to have a permutation at the bottom, permutation at the top, you need 2 of each number. If you do have that, it's always possible, is what I'm claiming, and you can like show why with a constructive proof. So since there are only going to be 2 of each number, we can like connect them, imaginarily connect them. So we'll have like, this is like the first combination we're interested in. Let's start with the 4. If we have just these 2 4s, we can just leave it how it is, because like one of them will be on the top, one will be on the bottom. So good, that's the 4s. What if we start with this pair here? Well, this might be okay, but it might not. It might also not be. So if we have this 1, we want to like combine it with this group here. We can imagine doing that. Now we've added this 5. We need to combine the 5 with this 3. Now we have this 3 adds this group, etc. So when we do this, each time we go like from top to bottom. So in this case, this is going to be like an A1, and this will be a B, because it goes, or like I guess it goes from 1 on the top to 1 on the bottom. So that's fine. So we can like label this 1 as an A, this 2 as a B. Well, like, yeah, okay. So like we want it to switch the height every time we go from left to right. That's the goal. Occasionally it won't though. So like there are 2 different types, there are 2 different orientations, and we're gonna have to flip either one of them so they all like go one way, or flip all of the other ones so they all go the other way for a given one of these cycles. So like in this example, this would be like version A, like the right one is on the top. 1 is like the interesting one we're doing, and that's on the top. Then we go to the 2. So in the next version, the 2 is on the bottom. So this is version B. And now we go to the 3. So now we just went to this. Now the 3 is on the bottom again. So this is version B again. Now we go to this third operation, is 5. 5's on the top. So this is an A. So what we need to do is we need to make either all of the B's turn into A's or all of the A's turn into B's. And yeah, that's the solution. So we pick whichever set is smaller. In this case, we're the same, so it doesn't matter. And we flip all of those. So in the samples, they flip the 2 B's. Another solution would be to flip the 2 A's. That would give you another equivalent solution. So yeah, that's those are the solutions I would use to these problems. I'm not entirely sure on my solution to F, so there might be a better, more solid way of approaching it that I haven't quite thought about. Anyway, sorry I couldn't like show you how I would compete the contest. I had other things going on, but at least I do have a solution video, so hopefully that was helpful. Yeah, that's all. Goodbye.